Today is February 3rd, 2017. This is AP Chemistry. I am Mr. Hobbs. Please feel free to subscribe to my channel. All right, so you three people that are out there watching. Okay. It is kind of weird to think that this is going through the whole world, though. I mean, possibly. I mean, it has the ability to. I mean, I don't think there's anybody in Timbuktu watching this, but okay. What did he say?
He said it's tough. Follow me at Daniel. Shout out to Martin.
All right. Now, today is Friday, so I guess it was yesterday. We were just talking, and we got through the first type of equilibrium problem, which is when they give you the concentration, they meaning the problem writer. So you have the concentration. Now, there are three different ways in which the concentration is given to you. They could just give you the equilibrium concentration. Now, again, if we're given Kc or Kp, that's at equilibrium. So to put it in the equilibrium expression, it has to be the equilibrium concentrations. And it will say that. At equilibrium, the concentrations were found to be, ... So you either just be given. Now that is, again, just super easy. It's actually too easy. It's so easy it's almost offensive. It's definitely an insult to your intellect if you were to do problems where they just gave you and you just had to plug it into a formula. There's no challenge whatsoever in that. There's not even any thrill of getting the right answer when doing something that simple. It's just simply saying, why am I having to do this? It's just busy work. Okay? So don't expect to see really any problems along those lines where it's just that straightforward. Okay? Because that's not fun. So the second type of the second way in which they give you the equilibrium concentrations is they give you the initial concentration, and then they give you an equilibrium concentration of one of the substances. Then you can use stoichiometry from the balanced equation, the coefficients, and you can figure out how much was added or lost to each substance, and you can figure that out. And I think we did a practice problem like that. Okay? And then the third way is simply, instead of saying there's a certain amount of equilibrium, a certain percent decomposing. And we'll look at and do a practice problem like that one in just a second. So that's the first type of problem. So let's look at some of those. So if we go, I think I'm just going to turn this on. If we look at page 654 in the white book, and look at question number 52. Or let's say 664. Where? Oh, those are additional problems. Let's turn back a page to page 662. 662. What are we doing? Oh. Y'all, nobody's watching y'all.
But you're YouTube famous.
Yeah. I was wondering what was going on. Y'all are going crazy. Help them, Lord. They need attention. Parents, if you're watching this, give your kids more attention. They need it. They want to know what we're doing at school. They want to know what you're learning. Okay? The equilibrium 2NO, this is number 29 on page 662. The equilibrium 2NO plus Cl2 goes to 2NoCl is established at 500 K. An equilibrium mixture of the three gases has partial pressures of 0.095, 0.071, and 0.28 for the three gases respectively. Calculate K, that's Kp, for this reaction. Okay? So first off, what's the equilibrium expression Kp going to equal? What's just the general expression for this? It's what over what? Products over reactants, right? So it's going to be what? NoCl squared divided by?
Pressure of NO squared.
Not plus. Times. Not squared. Just CO2. Okay, so we're using the coefficients raised to powers. Okay? And you cannot see that at all because of the glare. And so, PNOCl. So now we just need to plug in. This is plug it in, plug it in. Okay? So all we do now is just plug in the values that are given. The NOCl is given as, they list them in order, right? Three gases respectively. So the NOCl is the third one, so it's 0.28 squared divided by the NO, which is the first one, so it's 0.095 squared times the Cl2, which is the last one, or the middle one, which is 0.171. So we can just get the value. Simplest type problem there is. And someone on the calculator? 50.8. Does somebody agree with that? Okay, because we definitely have calculator issues in this class. Okay, 50.8. All right. Now we don't have to know units, but what would the units be on this if we were to calculate units? 1 over atmospheres, right? Or we could say atmospheres to the -1. Okay? Now again, generally speaking, you don't have to give a unit on K, but yeah, just simple manipulation there. So that's good. All right? So now, let's look at... Oh, you're all going to freak out again. Okay, now let's look at 31. Now 31 goes up onto both pages, so we're going to have to come back on that, but okay? So 31 says, a mixture of 0.1 mole, 0.05 mole, and 0.1 mole of water is placed in a 1 liter container. So if it's in a 1 liter container, what's the actual molarity going to be? 0.1, whatever it is, right? Because it's just divided by 1. Okay? The following equilibrium is established. So is this equilibrium concentrations? Okay, because it says it's placed in a 1 liter vessel. So it's put in, the equilibrium has been established. Then it says the following equilibrium is established. So these are initial concentrations. So we have the NO is going to be 0.1 molar. We did this exact one yesterday? Okay, well let's just do it again. Okay, because the other ones are in grams, so this one's good. Okay, so 0.1, we're going to get 0.05. So without looking then from yesterday, let's see if we can do it. And then 0.1 mole of water. So, those are initial. Which way does the reaction have to go and why? To the right. Why? Because how much N2 do we have? 0. 0. So it's going to go. So this change is going to be what? What's the other piece of information? What does it tell you up at the top right of the book on the problem? Of NO, right? So what must have the change have been? Minus 0.038. So since it's 1 to 1, what's this one going to be? Or 2 to 2? Minus 0.038. This one's going to be y half. 2 to 1, that's the coefficients. Okay? And then this is a 2, so this is going to be plus 0.038. So at equilibrium, then, we're going to get 0.012, 0.019, 138. Now we know the concentrations of all substances at equilibrium. Now we just plug it in, and that's what we did before. So we have this minus x plus x. We set up our ice table where we're given one of our equilibrium concentrations and our initial concentration. This is the second type of problem. Second type of way they give you the overall equilibrium, just in more indirect. Okay? So now let's look at the third way. Now we can go and turn to number 59 on 664. So now it's a very similar type problem. We're given 2 moles in a 2 liter. So if you put 2 moles into a 2 liter flask, what's the concentration? 1 molar. So my initial concentration is 1 molar. Now how much SO2 and Cl2 are being put in? How much SO2 and Cl2 is being put in? Why 0? Somebody else. It says it decomposes. Do they tell you that? What does it say? It just says when 2 moles of SO2 is placed in a flask, 56% decomposes. So they don't say anything about putting any of this. So we just know that that's 0 and 0. Okay? So what's the change going to be? 56%. So it's going to be minus 56%. Now, you might need to get your calculators out. I don't know. It's Friday afternoon. This mental math might be too tough. But what's 56% of 1? Okay? So 0.56. Okay? I am impressed.
I don't know what I did.
Okay?
I can see.
I can see why you're just totally wrong. Yeah, I can.
But it's minus.
No, like I was saying.
Okay, so it's going to be minus 0.56. So at equilibrium, our concentration of this is going to be 0.44. What's this going to be? This is going to be what? This is going to be what? Plus 0.56. This is going to be plus 0.56. So at equilibrium, we have 0.56, 0.56. Now we just plug it in, plug it in. So Kc is going to equal 0.56 squared divided by 0.44. Helps a little bit. And we get what? Okay, what would the units be on this one? Just molarity, because molarity squared divided by molarity is going to give you just molarity. So there's three ways in which they just give you the concentration. You're either going to just be given directly. They can just give you the initial concentration, then one of the concentrations at equilibrium, and then just using the coefficients figure out what the change is going to be for all the rest of them. Or they give you a certain percent reacts. And then you just multiply that percent by the initial amount and then just use the stoichiometry from there. So if this was a 2 in front of this would have been plus 1.12. Good math. Okay, 1.12. Okay? So, and then just whatever the coefficients are, then you just adjust appropriately for that. So then what you watched, I'm sure, last night was then, well, what happens if we're given the value of Kp and we have to find this? This is given concentrations, having to find Kp or Kc. What if we're given Kc and have to find the concentrations? So, we look at
Having lunch.
I'm not even here.
Keep our voices.
okay, unfortunately, I keep finding the good ones are the ones that are on two pages. Okay, y'all, here we go. We're going to look at number 43. So there's the equation. I'll write that on the board on the side. So there's number 40. So there's our equilibrium. So then they say, okay, well, Kc is given as this. So the equilibrium expression is 2 NO2s going to 2 NO plus O2. Okay? It says if the initial concentration of NO is 0.2, actually I think it's the other way.
It's 2NO goes to...
Yeah, I wrote it backwards. 2 NO plus O2 goes to...
It goes to N2O2.
N2 plus O2.
Goes to N2 plus O2. 43? Is that's the equation? 43 down the bottom?
Yeah.
Okay. Thought it was the other one. Okay. So, initial concentration of the NO is 0.2 molar. What's my initial concentration of N2 and O2? 0. Now this time I know Kc is given as 2.4 times 10 to the minus 3, or positive 3. Okay? So I need to know, well, the ultimate goal is, well, what are my equilibrium concentrations? That's what I want to know. Well, I know that Kc is equal to N2 times O2 all over NO squared. Right? So, I need these concentrations somehow, but I know Kc is equal to 2.4 times 10 minus 3. So, how much, the question is, how much of this, when we put this in, how much is going to go to the right? Do we know? But we don't really know, right? But what we do know is for every one of these, one of those is going to be formed. And for every one of these that is formed, how many of these are going to disappear? 2. So we can say it can be minus 2x plus x and plus x. So therefore, at equilibrium, we're going to have 0.2 minus 2x of this, x of that, and x of this. So we really only have one variable now. So now we can just plug this in, and we can say x times x all over 0.2 minus 2x squared is all going to equal 2.4 times 10 to the third. Now, this is where your fancy calculators are finally going to come to play. If you have your Inspire, you need to get it out. And we're going to learn how to use the solve function on your Inspire. You use it all the time? Okay? Well, it's going to make life easier. Now, this one actually is a perfect square because you get x squared. So if you want to, and actually when you go to college, they don't let you use this. I always thought they did, but they don't. Okay? Especially in the engineering class and stuff, you just have to would have to solve it as a quadratic. But this one you can eliminate because it's x squared over 0.2 minus 2x squared. You could take the square root of both sides, since it's a perfect square. So take the square root of both sides. Then you're just going to have x over 0.20 minus 2x is equal to the square root of this. So then you just use your algebra, manipulate. Then it's no longer a quadratic equation. But it's still a pain to do the algebra. You pay $120, $150 for this Inspire calculator. By golly, you might as well learn how to use it. Okay? Yeah. Texas Instruments, feel free to advertise on my page. Okay? I have some TI-89s. If you do not have an Inspire or a calculator with a solve function on it, those batteries are pretty much, make sure it's the one that has the good batteries that turns on. Okay? So, on your Inspire, if I'm correct, you go to your menu, you go to 3, which is algebra, and then you go to your solve function on that. Then you're just going to plug it in. Okay? So, you would just plug this in. Does everybody know how to plug it into your calculator? Okay? So, you're going to get 2 answers. One of them generally is negative. It can't be a negative number, so you can throw that one out. If you get 2 positive numbers, one of them will probably be bigger than 0.2, or when you multiply by 2x, it'll be greater than 0.2, which is irrational. You can't have more than what you started with react. Okay, so that's how you can know how to eliminate one of your answers. Okay? Are we getting an answer? Who has got an answer? What'd you get, Matthew? 0.01. 0.01? Somebody else have an answer? Here we go again, holiday.
Yeah, that's what I got.
0.099, which would be 0.1. 0.099 though?
Oh my God, yeah, I'm bad.
But if x is 0.099,
Yeah, it's 0.1, sorry. I got the answer.
yeah. So that means that 0.099, we'd really need to use 0.099 because times 2 is going to be 0.198, which means you'd only have 0.002 left of this. Now, notice that KC is 2400. It's pretty large. What is, hey, y'all, are y'all getting 0.099? Or watch. Bailey, yeah.
I mean, if you want, before you plug it in the first time, just click Control Enter when you're done.
No, I want everybody to learn how to do it, so I like this.
I forgot the
Yeah. Well, so I started to talk, and then I decided to. Okay, ladies, we're figuring out how to plug it all in. Well, I believe with Inspire, you have to use like 25 layers of parentheses in order to make it work right.
I didn't use that.
Did you get .989?
Yes.
0.9.
Point zero.
Oh, .09.
Yeah, .099. Now, hey, so x is equal to .099. Okay? So is that the answer to the question? What's the question asked for? What are the equilibrium concentrations of all three, of all the species involved, all the substances there? So that's where we come back to this right here. So the concentration of N2 equals the concentration of O2 equals .099 molar. That's what we let X equal. But the concentration of the NO is equal to 0.2 minus 2 times the .099. 99 times 2 is going to equal 198 or .198. Therefore, you subtract that, we're going to end up with .002 molar. So again, is this reactant favored or product favored? Okay? Because look, we have almost, if all 0.2 reacted, how much of this would we get? 0.1? No, if it all reacted, if 0.2 of this reacted, 2 makes 1, so 0.2 is going to make 0.1 and 0.1. But we're making .099. It's pretty close to 1. So it's going nearly to completion. How could I tell with this that it's going to do that? Above 1. Is it barely above 1? No, it's 2,400. It's way above 1. That's a big number. Therefore, it's very product favored. Very little of the reactant left at equilibrium. Okay, so when you're given the value of K and you have to find your equilibrium concentrations, you're definitely going to have to set up a nice table and just let X equal the amount that reacts, and then use your coefficients, whether it's minus X, minus 2X, plus X, and whatever. Okay? So let's look at you practicing doing one of these. Yes. Okay, now let's look at 65. Okay, what I have till 5 after, right? Yes. Time's flying by in here today. Throw a clock out the window, yeah. All right. Matthew, focus. So, I'm going to share with you on this, before we do the problem, there's two things that are going to be kind of oh my information. We're going to hear it. We're going to say, oh my, isn't that interesting? And then we're going to move on, and that's code again for no, it's not on the test, and therefore it's definitely not on the AP test. Okay? First thing is we want to talk about this compound right here and how it gets formed. Really the right-left reaction. Because if we look at this, we have pH3, which is going to be a pyramidal shape with a lone pair of electrons on the phosphorus. Just like NH3 is just phosphorus and nitrogen. Okay? That's going to react with the BCl3. Now, what is unique about boron trichloride? Okay, all I'm hearing is mumbling. Okay, say what? It doesn't require a filled octet. It's an exception to the octet rule to where we have less than 8 electrons. How many electrons does it need to have around it? 6. Okay, how do we know that? 13. It's really boron and aluminum are the two most common ones, but gallium would also do that. Okay? So we have an exception to the octet rule. Basically, it's got an empty space here. A place where it can bond. And so when these come together, actually the lone pair of electrons here gets shared by the boron. So both electrons of the single bond come from the same atom. When you put these together, it's called an adduct, where we then now have the two compounds came together. It's kind of like a composition reaction, but we would call this a coordinate covalent bond when we have the phosphorus and the boron, and then the Cl, 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 hydrogen, hydrogen, hydrogen. Both of these electrons came from the phosphorus. So old school called that a coordinate covalent bond. Now, because an electron is an electron is an electron, all electrons are the same. Doesn't matter if a boron electron, a phosphorus electron. There's still just one pair of electrons between the two. This is the same exact type, it's the same as a single covalent bond. Nothing changes. Okay? So nowadays they don't hardly even use the term coordinate covalent bond because there's no difference in this bond as there was in an ordinary covalent bond, so there's no need to differentiate it. It's just if you're trying to follow where the electrons came from, they both came from the phosphorus. But this actually is what we call the adduct, the thing that's been put together now because of the sharing of that lone pair of electrons. Group 13 elements are unique in being able to do that because they have that extra space to where they can handle another pair of electrons. Okay? So just kind of a unique thing there. It has absolutely nothing to do with being able to solve this problem. It's more of a Lewis structure type thing on how it all comes together. But it's just kind of a combination there. So, a coordinate covalent bond really is just a single bond, same strength, same characteristics as all that. So that's number one. Number two is the relationship between Kp and Kc. All right? You no longer have to know how to do the calculation, but in order to be able to do this problem, because they're giving us in terms of moles and liters, we need the value of Kc. So Kp, there's an equation, and this used to be given on the equation sheet, but we no longer have to do it for AP. But Kp is equal to Kc times RT raised to the delta N. Delta N is equal to moles of gas, products minus moles of gas reactant. And again, that was even given on the equation sheet, what delta N is. So, if we want Kc, Kc is going to equal Kp divided by RT raised to the delta N. Now, and by the way, what's R? That's the ideal gas law constant. That's our 0.0821. And T is the temperature. Since it's not delta T, what unit does T have to be in? Kelvin. So Kp is given as 0.052. divided by 0.0821 times the temperature of 60, which is going to be 333 K, raised to the, what's the product, moles of gas minus moles of gas? What's that, products minus reactants? What's that going to equal? 2. 1 plus 1 minus 0. Moles of gas, not just coefficients. I know you guys got the bad view today. So, somebody plug this into a calculator for me. Actually, let's say 2 or 3 people. Plug this into a calculator for me. Let's see how many answers we can get. 6.96. That's a different answer than what we got in the other class.
You got mine?
Okay? This is and you took this times this and squared the whole thing. And you used the parenthesis. Okay? Somebody look in the back of the book and see what the answer is.
I think the other class. It's not calculator.
15.65.
Yes.
Is this local? Oh, no, that's right. Answer is 7.0. 7.0.
Okay, 7.0, so 2 sig things. Okay. All right. So we leave that. So there's KC. Okay? Now we need to find out, as the vessel is charged with 0.0128. What do you think that means, charged with? What's that a weird or fancy way of saying? Added. Filled with. Okay? It's charged with. In other words, they just blew it in there somehow. 0.0128 moles in what volume? 0.5 liters. So that's dividing by a half, multiplying by 2, so this is going to be 0.0256 molar. So, moving over here. So now, KC, what's the KC expression going to be? Wow, we about out of time. pH3 times BCl3. Right? What about this one? It's a solid, so we don't include it. So it's just that. So now I need to know, okay, so what are my concentrations? Well, I have this, I have 0 of this, and they said they put some solid, but that just means that we have some of this now in the flask, but it's not in our equilibrium expression, so we really don't need to worry about the initial. So what's the change going to be? What's the change going to be of this? It's going to be minus x, right? So, KC is what do we figure it out to be? 6.96 times 10 to the minus 5 is equal to x times, well, actually, it's going to be plus x, sorry. It has to come this way because that's 0. X times 0.0256 plus x. Now, once again, if you don't have the fancy calculator, you have to use quadratic equation here, because you're going to get 0.0256x plus x squared. I don't think so. But I have 5 89s that we can use. as a classroom set.
They need that.
They do need batteries. I just bought batteries, so I'll put the batteries in them. I'll do that today. Okay? So somebody put this in. What does X equal? Anyone? X? I'm asking you. I don't know. 0.0028?
There's two positives.
Okay, but you can't be bigger than this.
The first one's negative.
Oh, yeah, never mind.
.002 what? 248. Okay, so this one is going to be plus 0.00248. So it's going to equal 0.0, was it 5 something? 504? If you add those two together, it's at 304? That's simple. 0.020. Okay? All right. So, when we're trying to deal with these problems, it's simply going to be setting up your ice table, plugging it in. You got to have your fancy calculator in order to be able to do that.
Is there a reason we didn't find KH3, BCl3
Because it's solid, and so we don't know its concentration at all. You just have to have some in the bottom, so we know that equilibrium got established. Without some of this in the bottom, we don't have equilibrium.
Sarah Nelson, Mason Giles, Jasmine Price, please come to